Hello and welcome to video lecture number 17, which covers section 1.10 day 3, inverse variation modeling. By the end of this lesson, you will be able to differentiate between inverse variation functions and other functions, and you will also be able to model situations with inverse variation functions. To get you thinking inverse variation and how it works, take a look at example 1. You're asked to think of and or sketch as many rectangles as you can that have an area of 36 square units. Using the formula for area, try to fill in all of the rows of the table with all possible combinations. In the table, here is one possible combination. If the length is 1 unit and the width is 36, these would produce an area of 36 square units. Now I will show you the remaining combinations. So here are all the possible combinations of dimensions, length and width that produce an area of 36 square units. Notice I did switch around values length and width and got a different possibility. Now please take a moment and pause the video and plot those points on the graph provided with length on the x-axis and width on the y. Take a moment to compare your graph with the one that I've displayed here. Does yours look like mine? Well, unlike direct variation, linear or nonlinear, the graph of inverse variation clearly does not pass through 0, 0, and in fact it will never be linear. So let's take a look at 1a. So what happened every time you calculate the x times the y in your table of values? Well, you probably already guessed it. We always get a 36. So any time that you multiply your two variable quantities together and get a constant number, this is known as inverse variation. So the information in the box summarizes inverse variation and what it may look like, and keep in mind that the terms varies inversely and inversely proportional also mean the same thing. Now the form of the equation is y equals kx, where k is still our constant of proportionality. However, as I showed you in the example above, by multiplying both sides by x in this equation, you also end up with y times x equals k. So either of these two representations here are the same thing. So if you're asked to identify inverse variation, look for either one of these forms. Furthermore, in an inverse variation equation, the independent variable x may also have an exponent. However, regardless of which case you have exponent or not with inverse variation, they are both non-linear situations. So example 1 asks us to look at various functions and determine whether they are inverse variation functions. So we are also asked to explain our result. So take a look at the function in example 1a. We have a table here. So I'm going to start by asking myself, does x times y produce some constant k every single time? If you multiply the x by the y in every single one of these table rows, what you'll notice is that you get very, very close to the value 12. Some are 11.999, some are 12.0001, something like that. Since they are very, very, very close to 12, we could say that this is a pretty good, accurate representation of inverse variation. So our answer for letter A would be yes, since x times y is approximately 12. So moving to example 1c, we look at the graph here and notice it's a straight line. So if you recall, inverse variation from example 1 will be a nonlinear graph. So to give you further detail here, Inverse variation is going to be a two-part disconnected graph that will either appear in quadrants 1 and quadrants 3 if the constant k is greater than 0, or it will show up in quadrants 2 and quadrants 4 if k is less than 0. Since this graph has neither of these characteristics, we will definitely say no, and the reasoning is shown here in the pictures. You could also put this into words if you prefer. So please take a moment to try example 1b, d, and e on your own and have those ready to check for tomorrow. So in example 2, we're asked to put the last two lessons together and determine whether these functions represent either direct variation or inverse variation, and potentially they could be neither of those two. So now we have to use what we learned before in addition to what you've just learned to try and put this all together. So I'll try a few of these with you, and I'll start with example 2b. Well, I have a table of values, so if I'm trying to attempt first to see if it's direct variation, I should check whether y divided by x equals k. If so, it's direct variation. If it's inverse variation, remember y times x would produce k. And if neither of these things happen, well then I would be left to suspect that it was neither. So let's run these tests. So as you inspect the values in the table, I hope you recognize that by multiplying the x and the y values, you don't get the same number every time. However, when I divide y by x every single time, with the exception of 0, 0, I end up producing the value 2. Since it's y over x equals 2, or if I multiply both sides by x, y equals 2x, notice the y-intercept is 0, it passes through 0, 0. This is what we would say direct variation. So I'm abbreviating here. So there is my explanation. So in letter D, I have a y equals mx plus b equation. Notice the y-intercept is negative 10, so that means it passes through the point negative 10. Also, since this is a straight line, it will not pass through 0, 0. In fact, it's going to pass through 0, negative 10. So this one is going to be neither, and it's going to be neither for the reasons I've suggested. It doesn't pass through 0, 0. Okay? And second of all, the reason why it's not inverse variation, because it's linear. Remember, if it's inverse variation, the graph would have to be non-linear. So when you say neither, please give a reason why it's neither direct variation nor inverse variation. So this would be my reasoning for letter D being neither. Moving to letter H, hopefully you can recognize here that if I multiply both sides by 5 of this particular equation, I end up producing y equals 5x. Well, since this is in the form y equals kx, it must be direct variation, and this is direct variation of the linear type. Please take a moment to try example 2a, c, e, f, and g on your own and have them ready to check for tomorrow. Please be sure to explain your answers. So in example 3, we're asked to write an inverse variation equation to model the situation as we did yesterday or the day before with direct variation. However, there may be additional questions that follow which we will use our equation to answer. So I'll do example 3a with you. You can try 3b on your own. So let's begin. It says a company has found that the demand for its product varies inversely as the price of the product. When the price is $3.50 per unit, the demand is 800 units. What will the demand be when the price is $4.75? So I've started by identifying varies directly, and remember that there are two variables, one coming before the varies inversely and one coming after. So I'm going to label these P for price and D for demand. And yes, as you may suspect, D is the same thing as Y, and P would be my independent variable. So we'll start by writing the general model. The general model will be D equals K over P. Now keep in mind, this is inverse variation, so that's why I'm writing it in this form. You may also be inclined to write it as D times P equals K, and in either case, we mean the same thing. So the next step is to find the variation constant, K, and I'll do so choosing the second model, D times P equals K. We are given two values, the 800 for demand and the 350 per unit as price, so I will multiply those together and that will give me the value of K. K is already solved for, so that's the nice thing about finding K in inverse variation equations. So when I multiply those two values, we come up with the variation constant as $2,800. So our third step in this process is then to write our general equation now with the value of K. So I will write D times P will equal $2,800, and that is our general equation that we will use to answer the question. So to determine what the demand will be when the price is $4.75, we will substitute that in to the equation we wrote in part 3. So I do not know D, the demand, but we do know that the price of the item is going to be $4.75, and we do know that total, the most that we can make is the 2,800, which is our constant in this problem. So now all we have to do is find D. We will do so by dividing both sides by $4.75. So by dividing those two, we get a decimal, but since our demand we're going to keep as a whole number, we will say the demand is approximately 589 units at that particular price of $4.75. So we have two answers here, the answer to the question and then of course the original equation that we wrote. Please try example 3b using the same reasoning. So this completes video lecture number 17. As always, take a moment to look back over any questions that we've done together or the ones you tried on your own, and please write down at least one question you have. Remember, at this point going forward, I will not sign your notes unless you have written a question and have attempted all examples. Thanks again for watching, and good luck.